The summer of 1816, a farmer in New England woke to find snow on the ground. It was June. Across Europe, the sky was the wrong color, red and orange where blue should have been. Harvests failed. Winters came twice. Riots broke out as food disappeared. People called it the year without a summer, and no one could explain it. It would be years before anyone connected it to the sound that had echoed across the ocean 14 months earlier, a sound so enormous it was heard hundreds of miles away, and so unfamiliar that the people who heard it had no idea what they were listening to. They had never heard anything like it before, because nothing like it had happened in living memory. On the other side of the world, on a remote island in Indonesia, something had just torn itself apart, and the shock wave from that single moment would reach into the lives of millions of people across 6 continents, most of whom would never know where the cold came from or why that summer never arrived. Tonight, we go back to that island, to the night that mountain in Indonesia changed the world. If you enjoy stories where science, history, and catastrophe quietly collide, consider subscribing. There are more moments like this buried in Earth's past than most people realize. Now, let's watch the day Earth's deadliest volcano woke up. Across Europe, armies were still moving through mud and smoke beneath the fading shadow of Napoleon Bonaparte. Couriers carried battlefield reports between capitals lit by candlelight, while ships crossed crowded trade routes loaded with grain, silk, coffee, and timber. The world in 1815 held nearly 1 billion people, yet most human lives still moved according to harvest cycles and rainfall. A failed growing season could empty villages as surely as war. In many places, survival remained tied directly to the thin layer of soil beneath bare feet. Far from the political centers of Europe, the Indonesian archipelago stretched across warm equatorial seas and thousands of scattered islands. Dutch colonial administrators maintained control through coastal ports and trading posts, watching the movement of spices and merchant vessels with far greater attention than the mountains rising beyond the shoreline forests. On the island of Sumbawa, Tambora stood quietly above everything around it, immense and green beneath drifting tropical clouds. At nearly 14,000 feet tall, it was among the highest peaks in the region, visible from great distances across the surrounding seas. For generations beyond memory, the mountain had remained silent. The last major eruption had occurred roughly 5,000 years earlier, so distant in time that no living tradition carried any warning forward. Grandparents told stories of storms, kings, migrations, and spirits of the forest, but none spoke of fire falling from the sky or ash turning day into night. Tambora had become part of the landscape itself, ancient and dependable, its volcanic slopes feeding deep layers of fertile soil into the surrounding kingdoms. Rice fields climbed the lower hillsides in careful terraces. Fruit trees grew heavily in the humid heat. Villages traded along narrow paths winding through dense vegetation filled with insects, birds, and the slow movement of river water descending from the mountain. The people living there spoke languages unfamiliar to outsiders, including the distinct Tambora language, which existed nowhere else on Earth. Their courts, customs, songs, and beliefs had developed in relative isolation, shaped by the rhythms of the island and the towering presence above them. European maps of Sumbawa during this period remained incomplete and uncertain. Large portions of the interior appeared as vague sketches bordered by coastlines sailors understood only from a distance. The Dutch East India Company viewed the region through commerce rather than geology. Ports mattered, shipping lanes mattered, seasonal winds mattered. A mountain resting silently above distant farming communities, inspired little curiosity from colonial officials concerned with trade revenue and naval movement. The science of the early 19th century also lacked the framework needed to recognize what Tambora truly represented. Volcanoes were understood as local disasters, destructive but limited, capable of burying towns or frightening nearby populations. The idea that an eruption on a remote Indonesian island could disturb weather patterns across continents belonged outside the imagination of the age. No instrument existed to measure stratospheric aerosols. No climate models connected atmosphere and agriculture into one planetary system. The mountain waited within that absence of understanding, silent beneath rain clouds and jungle heat, carrying unimaginable pressure deep beneath its slopes, while the world continued unknowingly around it. Long before fire appeared above Tambora, the changes began underground, hidden beneath layers of stone that had rested undisturbed since before recorded history touched the island. Deep below the forests and terraced fields, magma slowly shifted upward through fractures in the crust, releasing pressure in small, uneasy motions that traveled through the mountain like distant breathing during sleep. The first signs arrived quietly in 1812. People living along the slopes noticed faint tremors beneath their homes, subtle enough at first to resemble the passing weight of heavy rainstorms or the distant collapse of rock somewhere high above the trees. Then came the sounds. Low rumbles moved through the earth at irregular intervals, sometimes lasting only seconds, sometimes continuing long enough for cups of water to ripple beside cooking fires. Thin columns of steam began escaping from newly opened cracks near the summit. In the cool hours before sunrise, villagers could sometimes see pale vapor drifting against the darker outline of the mountain, dissolving slowly into the humid air above the jungle canopy. Local communities described the volcano as breathing. The phrase carried no scientific meaning, yet it reflected an instinctive recognition that the mountain no longer felt still. Over the next 3 years, the disturbances continued without settling back into silence. Small ash clouds occasionally appeared near the summit, spreading a faint layer of gray dust across leaves and rooftops before washing away in tropical rain. Livestock grew uneasy during periods of tremor activity. Dogs barked into the darkness for no visible reason. Monkeys moved downslope in unusual numbers. Flocks of birds abandoned nesting areas near the upper forests, filling the sky in sudden bursts of motion before disappearing toward the coastline. Reports eventually reached Dutch colonial authorities, stationed elsewhere in the archipelago, though they inspired little urgency. The administrators reading those messages had no established science of volcanology to guide them. Earthquakes, smoke, and eruptions belonged to the unpredictable behavior of islands already shaped by fire. No system existed to distinguish an ordinary volcanic disturbance from the early stages of one of the largest eruptions in recorded history. Then, on the evening of April 5th, 1815, Tambora broke its long restraint. A violent explosion erupted from the summit with such force that the sound traveled hundreds of miles across the sea. On distant islands, military officers believed artillery fire had begun somewhere offshore. Ships crossing the Java Sea adjusted course toward what captains assumed was a naval engagement hidden beyond the horizon. The sound moved outward through humid air in deep rolling waves, arriving long after sunset in places far removed from the mountain itself. Above Tambora, a towering column of ash and debris climbed approximately 33,000 feet into the atmosphere. Fine volcanic particles drifted westward on high winds, dimming the sunlight over neighboring islands by the following morning. Ash settled into rivers, coated vegetation, and gathered silently on the decks of anchored boats. Yet after the violence of April 5th, An uneasy stillness returned. The explosion had partially destabilized the magma chamber beneath the mountain, releasing pressure while also weakening the structure containing it. Nobody standing beneath the calmer skies that followed could see the deeper changes unfolding underground. The forests remained standing. The villages still held their evening fires. Some families who had fled during the ashfall gradually returned home, believing the mountain had exhausted itself. For 5 quiet days, Tambora waited again beneath the clouds. Evenings settled over Sumbawa beneath a sky that still appeared ordinary. Along the coastline, fishing boats rested in dark water, while cooking fires flickered between houses built from timber and woven palm. The air carried the familiar warmth of the tropics, heavy with salt and damp vegetation. Then, at approximately 7 o'clock on the night of April 10th, 1815, the mountain opened completely. Witnesses across the island described 3 separate pillars of flame rising from Tambora's summit at the same time, towering upward like enormous burning trees against the darkness. The mountain itself seemed to lose its solid shape. Sheets of incandescent rock poured down the upper slopes, while fountains of magma erupted into the air in continuous bursts. To observers many miles away, the entire peak appeared fluid, as though stone had transformed into fire. Below the summit, pressure that had accumulated over centuries released almost all at once. The eruption column surged upward with extraordinary velocity, carrying pulverized rock, volcanic gas, and ash high above the weather systems of the lower atmosphere. Within hours, the column reached approximately 140,000 feet, penetrating the stratosphere where powerful winds would later disperse its contents across the planet. The explosion produced an acoustic force so immense that sound traveled across oceans and islands with almost no loss of intensity. On Sumatra, more than 1,600 miles away, people heard deep concussive booms rolling through the night and mistook them for distant artillery. Closer to the eruption, the sound became physically unbearable. Residents on neighboring islands covered their ears in pain as shock waves rattled walls and shattered silence again and again with overwhelming force. Some survivors later reported temporary deafness lasting for days. While the eruption column climbed skyward, devastation spread outward along the ground with equal speed. Pyroclastic flows burst from the collapsing sides of the eruption column and descended the mountain in dense surges of ash, gas, and fragmented rock, heated to temperatures capable of instantly destroying organic tissue. Moving at nearly 450 miles per hour, the flows erased distance in moments. Forests vanished beneath rolling clouds of incandescent debris. Villages disappeared before anyone inside could flee. Within less than 10 minutes, the superheated currents reached the sea. The shoreline itself dissolved into steam and ash as the flows entered the water with explosive force. Everything within roughly 20 miles of Tambora's summit ceased to survive in recognizable form. Houses, roads, livestock, crops, and temples disappeared beneath layers of burning material that continued accumulating through the night. Among those lost were the people of the Tambora kingdom, their royal court, their spoken language, their songs, and oral histories ended during those same hours. No surviving community remained large enough to preserve the civilization that had existed on the mountain slopes for generations beyond memory. An entire branch of human culture vanished before dawn beneath volcanic ash and darkness. Far to the west on Java, Lieutenant Owen Phillips attempted to record what he witnessed from hundreds of miles away. Ash drifting through the atmosphere gradually blocked all remaining moonlight and starlight until the night became unnaturally opaque. Phillips later wrote that the darkness surrounding him had grown so complete he could not see his own hand held before his face. Along the flanks of a collapsing volcano, there exists a form of movement that resembles neither river nor storm. It travels low against the ground in dense surging clouds, carrying pulverized stone suspended within expanding gas, heated beyond the limits of ordinary fire. During the eruption of Tambora, these pyroclastic flows became the true instrument of destruction, spreading outward from the mountain with terrible speed through forests, villages, and coastlines in every direction. Inside the moving currents, temperatures approached 1,000 degrees Celsius. Rock fragments glowed within rolling clouds of ash, while compressed volcanic gases expanded violently downslope. Trees did not simply burn, their trunks fractured from thermal shock before igniting. Water inside leaves, roots, and living tissue flashed instantly into steam. The flows moved faster than any person or animal could escape, descending toward the coast at speeds approaching 450 miles per hour. Villages nearest the summit disappeared almost immediately beneath this advancing mass. Roofs collapsed beneath superheated debris before flames could fully spread through them. Livestock tethered in fields vanished alongside fences, pathways, irrigation channels, and cultivated land. Human bodies exposed directly to the flows experienced temperatures so extreme that survival became physically impossible within moments. The landscape itself changed state under the force of heat and pressure, losing familiar shape beneath accumulating layers of ash and fragmented stone. Less than 10 minutes after the eruption reached its climactic phase, the pyroclastic surges arrived at the coastline of Sumbawa. There, the mountain met the sea in a violent exchange of heat. Vast clouds of volcanic material poured directly into the water, generating explosive steam and pushing outward across the ocean surface in boiling turbulence. Sailors positioned miles offshore later described waves of unbearable heat striking their vessels even at considerable distance from land. Some boats suffered structural damage from pressure alone as the eruption continued through the night. The sea surrounding the island filled gradually with floating debris, shattered timber, and drifting pumice. Ash settled across the water in thick gray layers, while currents carried volcanic fragments outward into surrounding channels. Coastal vegetation blackened beneath falling material. Rivers flowing from the mountain transformed into dense streams of mud and ash that spread into bays already choked with debris from the eruption. Within this zone of devastation, entire human communities vanished permanently. The kingdom of Tambora, which had existed for generations along the mountain's slopes, ceased to survive as a functioning civilization. No known survivors remained capable of preserving its royal lineage, language, or oral traditions. On the western side of Sumbawa, the kingdom of Pakat suffered similar destruction beneath the expanding volcanic flows. Settlements that had once contained marketplaces, homes, and cultivated land disappeared beneath deposits many feet deep. Nearly 2 centuries later, archaeologists excavating the buried region uncovered fragments of that vanished world preserved beneath hardened ash. Inside one excavated structure, researchers found charred wooden beams collapsed beside ceramic vessels and domestic tools left exactly where they had rested during the eruption. Two human skeletons remained inside the house, fixed in the positions they occupied at the moment the pyroclastic flow entered the settlement. The scene resembled the preservation found at Pompeii, though separated by oceans and centuries. The immediate area devastated by Tambora covered roughly 200 square miles, transformed in a single night into a silent volcanic plain of ash, fractured stone, and buried memory. Beyond the burning slopes of Tambora, the surrounding sea had already begun to change shape. Water nearest the coastline trembled beneath the force of collapsing volcanic material pouring into the ocean at immense speed. Entire sections of shoreline vanished beneath surging clouds of ash and fragmented stone, displacing enormous volumes of seawater outward through the surrounding straits and channels of the Indonesian archipelago. The first waves moved invisibly through the darkness, spreading across the sea faster than any human message could travel. Fishing communities along distant coastlines continued their ordinary routines without knowledge of the catastrophe unfolding beyond the horizon. Lamps still glowed inside coastal homes on Lombok and Bali, while the water itself carried the energy of the eruption silently toward them. When the tsunami arrived, the sea rose suddenly along multiple shores almost at once. Wave heights reached approximately 13 feet in some locations, enough to overwhelm docks, flood low settlements, and sweep through harbors with crushing force. Wooden houses built close to the waterline broke apart beneath the surge. Canoes and fishing vessels snapped loose from their moorings and collided violently against one another before being carried inland by the retreating water. In several ports, larger ships were lifted entirely from the harbor and deposited far beyond their normal anchorage, stranded afterward among trees, roads, and fields. In Bali, Dutch colonial officials stationed at Singaraja recorded an especially strange sequence in the moments before the wave arrived. The harbor water began pulling away from the shore, exposing mud, rocks, and anchored boats resting suddenly on the sea floor. Fish flapped in the open air, where water had existed only minutes earlier. This withdrawal of the sea, now understood as drawback, lasted briefly before the returning wave surged inland with destructive force. For many victims, the tsunami came without any direct sensory connection to the eruption itself. They had not heard the explosions clearly. They had not seen the ash column rising above Tambora. The mountain remained distant and hidden beyond night and sea. Yet the eruption still reached them through moving water, carrying destruction into settlements untouched by fire or falling debris. At the same time, ash continued descending across the region while volcanic flows consumed the areas nearest the mountain. Together, these overlapping forces created a vast zone of devastation spreading across islands, coastlines, and sea routes simultaneously. Survivors, escaping one danger, often encountered another. Wells filled with ash became undrinkable. Harbors disappeared beneath floating pumice and wreckage. Shorelines altered shape beneath layers of volcanic sediment deposited by retreating water. During the first 24 hours alone, an estimated 10,000 to 11,000 people died from the eruption's direct physical effects. Many more remained missing beneath collapsed buildings, buried villages, or coastal waters carrying debris far from the original disaster zone. In the weeks that followed, ships crossing the Java Sea encountered floating remains of shattered homes, uprooted trees, and bodies drifting among fields of pumice stone spread across the surface of the water. Even at distances approaching 1,200 miles from Tambora, instruments and coastal observations detected unusual wave motion connected to the eruption. The sea itself had absorbed part of the mountain's violence and transmitted it outward across the surrounding world, long after the initial explosions had faded into distant thunder beyond the horizon. Morning never truly arrived after the eruption. Across Sumbawa and the surrounding islands, people waited for the gradual whitening of the eastern horizon that normally announced dawn, yet the sky remained sealed beneath layers of drifting volcanic ash. The sun still existed above the atmosphere, but its light could no longer penetrate the dense particulate veil spreading outward from Tambora. Within 24 hours, darkness covered an area extending roughly 300 miles in every direction from the mountain. This was not the dimness of storm clouds or the soft obscurity of tropical rain. The air itself had become saturated with microscopic fragments of pulverized rock suspended so densely that daylight disappeared entirely. Ash absorbed and scattered incoming sunlight until day and night became almost impossible to distinguish. Survivors later described 3 consecutive days during which natural light vanished completely. No sunrise marked the beginning of morning, no sunset closed the evening. At night, even the stars disappeared behind the volcanic haze. Lamps and fires provided only faint circles of illumination, swallowed quickly by the surrounding blackness. In some villages, people moved by touch rather than sight, following walls, tree trunks, or familiar pathways buried gradually beneath ashfall, accumulating hour after hour. The natural rhythms that guided animal behavior also collapsed beneath the altered sky. Birds that normally greeted dawn remained silent or flew aimlessly in confused patterns before settling again. Insects emerged at irregular intervals, unable to follow the absent cycle of sunlight. Livestock refused to graze or wandered restlessly through fields already disappearing beneath thick volcanic deposits. Along the coastline, fish floated dead near the surface where ash and debris contaminated shallow waters. Agriculture across the region failed almost immediately. Rice paddies vanished beneath layers of ash heavy enough to crush young plants under their weight. Fruit trees lost branches beneath the accumulating material coating leaves and stems in suffocating gray dust. Vegetable crops that had fed entire communities only days earlier became unusable within hours. Irrigation channels clogged with sediment, transforming fertile land into silent fields buried beneath volcanic residue. Freshwater sources suffered equally. Streams descending from the mountain carried ash into reservoirs, wells, and rivers across Sumbawa and neighboring islands. Water collected from open containers turned abrasive and bitter with suspended particles. Survivors strained liquid through cloth or boiled it over weak fires, though many sources remained contaminated beyond practical use. Those who escaped the eruption's immediate violence now faced dehydration and hunger spreading quietly through the surviving population. Meanwhile, the ash cloud continued expanding across the region on upper atmospheric winds. Fine volcanic particles settled over an estimated 500,000 square miles, reaching islands far beyond the immediate disaster zone. The sky dimmed across distant coastlines beneath thin drifting haze carried steadily westward and northward from Tambora. At sea, navigation became increasingly difficult. Ships crossing the Java Sea encountered vast floating fields of pumice released during the eruption. The porous volcanic stone accumulated in dense rafts stretching across the water surface, scraping against hulls and slowing movement almost to a standstill in some areas. Sailors described the strange sensation of steering through what resembled drifting islands of pale rock scattered across otherwise open water. The darkness that settled over Sumbawa in April of 1815 marked more than the aftermath of a volcanic eruption. It became the opening condition of a much larger transformation already beginning to move outward through climate, agriculture, disease, and human history itself. High above the eruption itself, beyond the collapsing forests and buried coastlines, the atmosphere was undergoing a quieter transformation. The violence visible from the ground represented only part of Tambora's power. Much of the eruption's lasting influence traveled upward into layers of air rarely touched by ordinary weather, entering a region where volcanic material could remain suspended for extraordinary lengths of time. Among the gases released during the eruption was an estimated 60 megatons of sulfur dioxide. As the eruption column penetrated deep into the stratosphere, this gas spread into cold, stable air far above rain clouds and seasonal storms. In the lower atmosphere, sulfur compounds are usually washed out relatively quickly through rainfall. At stratospheric altitude, however, the process slows dramatically. The sulfur dioxide gradually reacted with water vapor and oxygen, forming vast quantities of sulfate aerosols, microscopic droplets capable of drifting around the planet for years. These aerosols did not darken the sky in the same manner as falling ash. Instead, they formed a thin, reflective veil surrounding the Earth at high altitude. Sunlight approaching the planet encountered this suspended layer before reaching the surface. Part of the incoming solar radiation scattered back into space, reducing the amount of warmth and visible light able to pass through the atmosphere below. Modern climate science refers to this process as volcanic winter. Tambora produced the most severe example of volcanic winter recorded during human history. Within months, stratospheric wind patterns distributed the aerosol veil across much of the globe. The circulation of the upper atmosphere carried Tambora's chemical signature across oceans and continents with remarkable efficiency, transforming a regional eruption into a planetary atmospheric event. The scale of material ejected from the volcano remains difficult to visualize even today. Tambora expelled approximately 160 cubic kilometers of ash, fragmented rock, pumice, and volcanic gas into the atmosphere and surrounding region. By comparison, the eruption of Mount St. Helens in 1980, one of the most famous volcanic events of the modern era, released roughly 1 cubic kilometer of material. Tambora exceeded that volume approximately 160 times over. For days after the eruption, fine particles remained suspended in the upper atmosphere, while heavier material settled slowly across land and sea below. Some fragments traveled enormous distances before descending. Others remained aloft, circulating invisibly within the stratosphere where no human observer could directly follow their movement. The eruption had effectively altered the optical and thermal behavior of the atmosphere itself. Globally, scientists estimate that the aerosol layer reduced the amount of sunlight reaching Earth's surface by approximately 5 to 10%. Numerically, the reduction appears modest, almost delicate when expressed as a percentage. Yet, agricultural societies of the early 19th century depended upon remarkably stable seasonal patterns. Slight shifts in temperature, rainfall timing, or available sunlight could determine whether grain ripened fully before harvest or failed entirely in the field. Plants operate through narrow biological margins shaped by temperature and light. A shorter growing season, a colder summer, or diminished sunlight during critical phases of crop development could ripple outward through entire food systems. In 1815, most of humanity remained directly tied to those systems, with little stored surplus and limited capacity to absorb widespread agricultural disruption. The atmosphere above Tambora had become a global filter, quietly changing the relationship between sunlight and the surface of the Earth. In the summer of 1816, people across the northern hemisphere began waking into seasons that no longer behaved correctly. The familiar rhythm between spring warmth and autumn cold seemed to loosen without explanation, replaced by skies and temperatures that shifted in unsettling ways from week to week. Farmers studied their fields with growing uncertainty, while church bells rang through villages, surrounded by crops failing beneath weather no one recognized. By then, the sulfate veil produced by Tambora had fully encircled much of the globe. Suspended high in the stratosphere, the aerosol layer reflected enough sunlight away from Earth to alter atmospheric circulation patterns across continents and oceans. Average global temperatures declined by roughly zero point 0.4 to zero point 0.7 degrees Celsius. The numerical change appeared small when measured scientifically, yet planetary systems operate through delicate balances. A slight reduction in heat reaching the surface was enough to disturb winds, rainfall, seasonal timing, and agricultural stability on an immense scale. In New England, cold arrived repeatedly during months that should have belonged to growth. Snow fell during June across parts of Massachusetts, New Hampshire, and Maine. Frost appeared in every month of the year somewhere within the region. Farmers in Vermont watched cornfields blacken after sudden freezes struck in July, destroying crops that had appeared healthy only days earlier. Thin layers of ice formed across ponds during mornings that should have carried midsummer warmth. Farther north in Quebec, snowstorms lingered deep into the growing season. In some areas, snow falling during June remained visible along shaded ground through much of the summer, melting only gradually beneath weak sunlight and persistently cool air. Communities dependent on short agricultural seasons found themselves with little margin for failure. Livestock feed diminished. Harvest expectations collapsed. Across Europe, the altered climate expressed itself differently. Germany experienced repeated flooding along the Rhine River as abnormal precipitation patterns saturated the landscape. Roads dissolved into mud beneath endless rainfall, while river traffic struggled against swollen currents. In France and Switzerland, grain harvests deteriorated severely. Wheat and rye failed to mature properly in cold, damp conditions, leaving stores dangerously low before winter had even begun. People searching for language to describe the strange year created names shaped by exhaustion and disbelief. In North America and parts of Europe, 1816 became known as the year without a summer. Others called it 1800 and froze to death, a phrase carried through newspapers, letters, and private journals written beneath darkened skies. The cooling itself did not spread evenly across the planet. Some regions endured persistent cold, while others faced relentless storms or prolonged drought. The atmosphere behaves as an interconnected system of moving energy, and Tambora's aerosol veil disrupted those movements differently depending on geography and season. Monsoon cycles shifted, jet streams altered course, rain arrived at unusual times or failed to arrive at all. Yet beneath these regional differences, one shared reality connected affected communities everywhere. Agricultural societies depended upon consistency built over generations of observation. Planting schedules, grazing patterns, grain storage, and food transport all relied on expectations shaped by centuries of relatively stable seasonal behavior. Tambora interrupted those expectations simultaneously across multiple continents. The result was not simply colder weather. It was the collapse of predictability itself, carried invisibly through the atmosphere from a distant mountain. Many of the people suffering beneath these altered skies had never heard named. The failure of harvests did not arrive everywhere with the same appearance. In some regions, fields drowned beneath endless rain. In others, cold lingered too long into spring, delaying planting until crops no longer had enough sunlight to mature properly before autumn returned. Yet, across continents separated by oceans and languages, the result slowly became identical. Granaries emptied, food prices climbed, hunger spread outward from villages into entire nations. By the end of 1816, famine conditions had emerged across large parts of Europe and North America simultaneously. Agricultural societies of the early 19th century possessed few safeguards against consecutive failed harvests. Most communities relied almost entirely on local grain production, seasonal livestock feed, and predictable weather patterns refined through generations of observation. Tambora's volcanic winter disrupted all three. In Ireland, potato and oat harvests suffered severe damage from persistent cold and rain. Rural communities, dependent upon these crops, entered winter with dangerously reduced reserves. Historians later recognized this period as an early warning of the vulnerability that would become tragically visible again during the Great Famine of the 1840s. The land itself remained fertile, yet the atmosphere above it no longer behaved according to expectation. Across Wales, grain prices rose more than 300% within a single year. Bread, once ordinary and accessible, became increasingly difficult for working families to obtain. In France, food shortages intensified existing political and economic tensions left behind after the Napoleonic Wars. Grain convoys traveling between regions attracted desperate crowds, and riots broke out in multiple cities as hunger deepened through the population. Germany endured some of the harshest conditions in Europe. Failed harvests, combined with soaring prices, forced many families to abandon farms that could no longer sustain them. Historians trace the beginning of large-scale German emigration to North America directly to the famine conditions following Tambora. Entire communities packed belongings into wagons and riverboats before eventually crossing the Atlantic in search of more stable agricultural land. In Switzerland, starvation spread through isolated rural cantons where mountain geography complicated transportation and food distribution. Government authorities declared a state of emergency as livestock weakened and grain supplies diminished. Lakes and roads already affected by abnormal weather slowed relief efforts further. The atmospheric disruption extended beyond Europe. In China's Yunnan province, altered rainfall patterns and colder conditions damaged rice harvests repeatedly across 3 consecutive years. Agricultural systems that normally supported dense populations struggled beneath shifting seasonal behavior. India experienced changes in monsoon circulation severe enough to contribute to cholera outbreaks in vulnerable regions. Flooding and drought appeared in unstable sequence, damaging crops and contaminating water systems. As weakened populations moved through expanding colonial trade networks, the disease began spreading outward along shipping routes that connected Asia, the Middle East, and eventually Europe. North America faced its own migrations shaped by scarcity. Farmers throughout New England abandoned, exhausted, or frozen farmland and moved westward toward the interior of the continent. Many historians believe Tambora indirectly accelerated settlement across the American Midwest by making traditional farming regions temporarily unsustainable. Modern researchers estimate that famine and disease connected to Tambora may have killed somewhere between 70,000 and 1 million people. The uncertainty reflects the difficulty of tracing deaths scattered across continents and years. Hunger leaves quieter records than war, yet its movement through human history can reshape the world just as completely. Along the riverbanks of Bengal, the seasons began arriving in broken patterns after the eruption. Floodwater spread across farmland during months that should have remained manageable, then withdrew too quickly beneath unusual heat and dryness. Villages built beside the delta's branching waterways found themselves surrounded by contaminated pools, damaged crops, and unstable drinking supplies. The atmosphere altered by Tambora had begun changing conditions far beyond the volcanic horizon. Before 1817, cholera remained largely confined to the Bengal region of India. The disease could devastate local populations living near contaminated water systems, yet it had not become a recurring international threat. Most outbreaks stayed regionally contained within environmental conditions favorable to the bacterium that caused the illness. The years following Tambora transformed those conditions dramatically. Disrupted monsoon cycles during 1816 and 1817 produced alternating floods and drought across parts of the Bengal Delta. Heavy rains overwhelmed sanitation systems and carried waste into rivers, ponds, and wells relied upon for drinking water. When floodwaters receded, stagnant pools remained beneath tropical heat, allowing cholera bacteria to multiply rapidly in warm, contaminated water. At the same time, many populations across Asia were already weakened by hunger linked to failed harvests and climatic instability. Malnutrition reduces the body's ability to survive infectious disease, especially illnesses causing severe dehydration. Communities already struggling with food shortages became increasingly vulnerable as cholera spread through crowded settlements connected by river trade and migration. What allowed the outbreak to expand beyond Bengal was the growing network of 19th century commerce. Colonial shipping routes linked India to ports across Southeast Asia, the Middle East, East Africa, and eventually Europe. Merchant vessels carried textiles, spices, grain, soldiers, laborers, and infected passengers along the same maritime corridors. Rivers flowing into the Indian Ocean became part of a much larger transportation system binding continents together. Cholera moved outward through those connections. By the 1820s, outbreaks had reached Persia and Russia. Caravans, military campaigns, and commercial traffic carried the disease steadily across borders that could not contain contaminated water or infected travelers. Cities unfamiliar with cholera struggled to understand what they were facing. Physicians debated theories involving climate, bad air, or urban crowding, unaware that the disease spread primarily through polluted water systems. During the 1830s, cholera entered Western Europe and North America. Epidemics appeared in major cities, including London, Paris, and New York, where dense populations and poor sanitation allowed the disease to spread rapidly. Panic often accompanied outbreaks because the illness struck with frightening speed, draining the body through severe dehydration within hours or days. The first global cholera pandemic killed tens of thousands of people directly, though exact numbers remain uncertain across such vast geographic distances. More significantly, it established cholera as a permanent international disease capable of moving repeatedly through interconnected populations. Modern epidemiologists studying historical climate data increasingly connect Tambora's eruption to the environmental instability that helped trigger this transformation. The volcano did not create cholera, but it disrupted rainfall, agriculture, nutrition, and water systems across vulnerable regions at precisely the moment global trade networks were expanding. A volcanic eruption on a remote Indonesian island may have permanently altered the disease landscape of the 19th century, reaching into human biology through the atmosphere itself. Across the roads of Europe in the years after Tambora, an unusual silence began settling over travel routes, once filled with the steady rhythm of hooves. Fewer wagons arrived at market towns. Fewer plows moved through fields. In villages already strained by failed harvests and rising food prices, horses were disappearing alongside grain reserves and livestock feed. In the early 19th century, horses occupied a role modern societies now distribute across engines, trucks, trains, and machinery. They pulled agricultural equipment through farmland, transported goods between cities, carried mail across long distances, powered trade networks, and moved people through nearly every level of daily life. A healthy horse represented labor, mobility, and survival all at once. The famine conditions following Tambora placed enormous pressure on that system. As harvests failed across Europe and North America, the cost of grain and hay rose dramatically. Families struggling to feed themselves could no longer spare precious food for draft animals, requiring large daily amounts of fodder. Owners began selling horses they could not maintain. Others slaughtered weakened animals before winter arrived. Across rural regions, horse populations declined rapidly beneath the combined weight of starvation and economic collapse. The loss created consequences extending far beyond transportation. Fields without horses became more difficult to cultivate efficiently. Trade slowed as fewer wagons carried supplies between towns. Urban movement became increasingly expensive. In some places, the shortage of surviving horses deepened the existing food crisis because fewer goods could be transported quickly across damaged agricultural regions. Among those observing this changing landscape was a German inventor named Karl von Drais. Living within a Europe reshaped by famine and scarcity, von Drais recognized that dependence upon horses carried a dangerous vulnerability. If animal transportation could collapse during a period of environmental disruption, an alternative form of personal mobility might become necessary. In 1817, only 2 years after Tambora's eruption, von Drais introduced a machine unlike anything commonly seen on European roads. He called it the Lauf machine, or running machine. Constructed primarily from wood, the device consisted of two inline wheels connected by a frame with handlebars for steering. Riders sat astride the machine and propelled themselves forward by pushing against the ground with their feet. The invention lacked pedals, chains, or gears. Movement depended entirely upon alternating strides that allowed the rider to glide briefly between pushes. Yet the principle underlying the machine was revolutionary. Human beings could travel efficiently on two wheels without relying upon animal power. Demonstrations of the Lauf machine attracted curiosity across parts of Europe. Some observers considered it impractical or strange, while others immediately recognized its possibilities. Over subsequent decades, inventors refined the design gradually, adding pedals, metal frames, rubber tires, and eventually the mechanical systems associated with modern bicycles. The connection between Tambora and the bicycle remains one of history's most remarkable chains of consequence. A volcanic eruption in Indonesia altered global climate patterns, contributed to famine conditions severe enough to kill vast numbers of horses, and indirectly inspired the search for an alternative form of transportation. From that search emerged the earliest ancestor of the bicycle, a machine that would later reshape cities, labor, recreation, and personal mobility across the world. Sometimes technological change does not emerge from ambition alone. Sometimes it begins quietly inside a season of scarcity when survival itself demands a different way forward. Rain fell constantly over Lake Geneva during the summer of 1816. Clouds gathered low across the mountains surrounding the water, dimming afternoons into an early gray twilight that lingered long after morning should have brightened the sky. The season carried an unfamiliar chill through Switzerland, and storms arrived with such persistence that outdoor travel became difficult for weeks at a time. On the northern shore of the lake stood the Villa Diodati, a large rented house overlooking the water and distant alpine slopes. Inside, a small circle of young writers passed long evenings sheltered from the strange weather unfolding beyond the windows. Among them were the poet Percy Bysshe Shelley, his future wife Mary Godwin, and the already famous Lord Byron, whose reputation for scandal and literary brilliance followed him across Europe. The cold summer trapping them indoors was not an isolated Swiss anomaly. High above the atmosphere, Tambora's aerosol veil continued scattering sunlight and altering climate patterns across the northern hemisphere. The result in parts of Europe was a season of relentless rain, unstable temperatures, and darkened skies that seemed strangely disconnected from ordinary summer weather. At the villa, the group read aloud from collections of German ghost stories while storms moved across the lake outside. Candlelight reflected faintly against windows streaked with rain. Conversation drifted through philosophy, science, poetry, and recent experiments involving electricity and the possibility of stimulating dead tissue through electrical currents. During one especially stormy evening, Byron proposed that each member of the gathering attempt to write a supernatural tale of their own. Mary Godwin was only 18 years old. For days, she struggled to discover an idea strong enough to match the atmosphere surrounding them. Then, during a restless night shaped by conversation, imagination, and the oppressive weather beyond the villa walls, she conceived the image of a scientist assembling life from dead matter. In her vision, human ambition crossed into forbidden territory, creating something powerful and tragic that could not be controlled once awakened. 2 years later, after marrying Percy Shelley, she published the story under the name Mary Shelley. The novel was Frankenstein, now widely regarded as the first true work of science fiction in literary history. Its themes of creation, responsibility, isolation, and technological ambition would echo through literature, cinema, and scientific imagination for centuries afterward. The same dark summer influenced Byron as well. During his stay beside Lake Geneva, he composed a poem titled Darkness, a haunting vision of planetary collapse in which sunlight disappears and civilization descends gradually into ruin. The imagery carried an eerie resemblance to the atmospheric conditions produced by volcanic winter. Byron wrote, "The bright sun was extinguished, and the stars did wander darkling in the eternal space," describing a world where familiar natural order dissolves beneath dim skies and failing ecosystems. Neither Byron nor Shelley fully understood the planetary mechanism responsible for the weather surrounding them. Tambora remained a distant eruption on a remote island many Europeans barely knew existed. Yet, its effects had already entered the emotional and intellectual atmosphere of the age, shaping imagination as surely as it shaped climate. The eruption did more than destroy harvests or alter temperatures. It reached invisibly into literature itself, influencing works that would define Western storytelling for generations. A mountain collapsing in Indonesia helped create one of humanity's enduring myths about science, creation, and the uneasy boundary between discovery and consequence. Evening light across Europe began behaving differently after the eruption. Sunsets lingered longer along the horizon, spreading through the atmosphere in layers of deep orange, crimson, and copper, unlike the softer tones people had known before. Twilight seemed stretched beyond its ordinary boundaries, remaining suspended in the sky long after the sun itself had disappeared below the landscape. The change originated high, above the weather systems of Earth. Sulfate aerosols released by Tambora remained suspended throughout the stratosphere, scattering sunlight as it passed through the atmosphere. Different wavelengths of light bent and dispersed unevenly through the aerosol veil, producing vivid optical effects visible across much of the northern hemisphere. Around the sun and moon, faint halos sometimes appeared within thin clouds. At dawn and dusk, the sky often glowed with intense reds and yellows that seemed almost unreal in their saturation. Artists noticed. Beginning in the years immediately following 1815, painters across Europe started capturing skies filled with unusual atmospheric color and dramatic illumination. Their canvases reflected not only changing artistic taste, but a planet whose atmosphere had physically altered the appearance of light itself. Among the most striking examples were the works of the British painter Joseph Mallord William Turner, known widely as J.M.W. Turner. His paintings from this period contain skies flooded with luminous orange, scarlet, and gold tones spreading across oceans, harbors, and distant horizons. For many years, art historians interpreted these colors primarily as expressions of Turner's imagination and emotional style. Yet, modern scientific research suggests the skies he painted may have been unusually accurate observations of post Tambora atmospheric conditions. In 2014, researchers publishing in the journal Atmospheric Chemistry and Physics analyzed the color composition of Turner's sunset paintings alongside known records of volcanic aerosol concentration in the atmosphere. Their study identified a statistically significant relationship between major volcanic eruptions and the intensity of red coloration appearing in his artwork. The atmosphere altered by volcanic particles had likely influenced the physical light Turner observed while painting. Other European artists from the same era reveal similar atmospheric transformations in their work. The German painter Caspar David Friedrich often depicted landscapes beneath strange glowing horizons and heavy, luminous skies. In England, John Constable's cloud studies and sunset scenes from the early 19th century contain atmospheric qualities that align closely with periods of elevated aerosol concentration following major eruptions. The Romantic movement in European art had already been drawn toward nature's scale, mystery, and emotional intensity. Yet, the altered atmosphere following Tambora may have deepened those visual tendencies in ways the artists themselves never fully understood. Painters attempting simply to record the world around them found that the world itself had changed color. What people considered beautiful during those years may have shifted partly because sunlight passing through the atmosphere had become physically different. The visual language of the period, its glowing horizons, dramatic clouds, and radiant twilight scenes, emerged not only from artistic philosophy, but from volcanic chemistry unfolding invisibly above the earth. Tambora's influence extended beyond climate and agriculture into perception itself. A mountain collapsing in Indonesia changed the appearance of European skies for years afterward, and generations of artists carried those altered skies onto canvas. The eruption became preserved not only in ice cores and historical records, but in paint layered carefully across linen beneath candle-lit studio windows. Before Tambora, most people understood weather as something regional and temporary. A harsh winter belonged to one country, a drought belonged to one valley. Storms were recorded locally, discussed locally, and endured locally. Few scientists imagined that an eruption on a distant island could alter the atmosphere of the entire planet for years afterward. The events following 1815 forced that assumption to change. As reports spread across Europe and North America, describing failed harvests, strange, cold, relentless rain, and summer frosts, natural philosophers began recognizing patterns too widespread to dismiss as coincidence. Communities separated by oceans were experiencing disturbances at nearly the same time. The atmosphere no longer appeared fragmented into isolated regional systems. It began to look connected. The idea was not entirely new. After the eruption of Iceland's Loki volcano in 1783, Benjamin Franklin had suggested that volcanic particles suspended high in the atmosphere might cool the climate by reducing incoming sunlight. His proposal attracted little lasting attention. Scientific instruments remained limited, and no coordinated international weather records existed to support the theory convincingly. Tambora provided evidence on a scale impossible to ignore. The cooling following the eruption left traces across agriculture, diaries, shipping records, and temperature observations throughout multiple continents. Scholars began comparing weather reports between countries more systematically, searching for relationships between atmospheric behavior occurring across great distances. This gradual shift helped shape the early foundations of meteorology as a coordinated scientific field. Governments and scientific societies expanded efforts to collect standardized weather data during the decades that followed. Thermometers, barometers, and rainfall measurements became increasingly important tools for understanding patterns extending beyond local observation. Networks for sharing climate information between cities and nations slowly emerged, allowing scientists to study weather as part of a larger global system. Tambora also transformed the scientific study of volcanoes themselves. Before the 19th century, eruptions were often treated primarily as isolated natural disasters or geological curiosities. After 1815, researchers increasingly recognized that volcanic events could influence ecosystems, agriculture, disease, migration, and climate far beyond the immediate eruption zone. The field, now known as volcanology, began developing more formal methods for studying magma chambers, eruption mechanisms, ash dispersal, and volcanic gases. Scientists sought to understand not only why eruptions occurred, but how their effects traveled through the atmosphere and across human societies. Modern climate science still relies heavily on lessons drawn from Tambora. Researchers studying volcanic winter use the eruption as one of the clearest historical examples of how sulfate aerosols cool the planet by reflecting sunlight back into space. The same atmospheric mechanisms appear in models of nuclear winter, which examine how smoke and particles from large-scale nuclear conflict could reduce global temperatures and disrupt agriculture worldwide. Tambora has also influenced debates surrounding solar geoengineering, the controversial proposal to intentionally release reflective particles into the stratosphere to counteract global warming. Scientists examining these ideas often study volcanic eruptions because nature has already conducted the experiment. Many of the scientific systems used today to monitor climate and volcanic hazards trace part of their intellectual origin to the questions raised after 1815. The eruption forced humanity to see the atmosphere differently, not as separate skies hanging over separate nations, but as one continuous planetary system through which light, ash, wind, and consequence move together around the Earth. For generations after the eruption, the kingdom of Tambora survived mostly as an absence. Dutch colonial documents mentioned vanished settlements and depopulated slopes, while oral traditions passed quietly between communities on Sumbawa spoke of villages erased beneath ash and fire. Yet almost no physical evidence remained visible on the surface. Forest growth and volcanic deposits concealed the old kingdom so completely that its people began to seem almost legendary, as though the mountain had swallowed not only lives, but memory itself. Nearly 2 centuries later, in 2004, archaeologists returned to the slopes, searching for traces of the lost civilization. The expedition was led by volcanologist Haraldur Sigurdsson, whose earlier research on Tambora had already helped reconstruct the scale of the eruption. This time, the goal extended beyond geology. Beneath the ash, researchers suspected an entire human world might still remain preserved. The landscape revealed little at first. Thick volcanic deposits covered the terrain in layers, hardened by time and tropical rainfall. Dense vegetation obscured older settlement patterns almost completely. To search beneath the surface, without extensive excavation, the team used ground-penetrating radar, a technology capable of detecting buried structures and unusual underground formations through reflected electromagnetic signals. The instruments began identifying anomalies beneath the ash. When excavations started, archaeologists uncovered the remains of a village buried under approximately 10 feet of volcanic material. What emerged from the earth stunned researchers immediately. The eruption had preserved the site with extraordinary completeness, sealing everyday objects beneath dense ash in much the same way Vesuvius preserved parts of Pompeii nearly 2,000 years earlier. Inside the buried structures, ceramic vessels still contained carbonized food left behind during the final moments before destruction. Iron tools remained positioned where they had once been used. Bronze containers survived beneath collapsed roofing material. Among the discoveries was a complete bronze bell, delicately crafted and remarkably intact despite the violence that had buried it. Two human skeletons were found inside one structure, preserved in the positions they occupied when the eruption overtook the settlement. The victims appeared to have died instantly as volcanic material engulfed the village. Their remains transformed the excavation from an archaeological survey into something quieter and more intimate, a direct encounter with lives interrupted in a single night during 1815. The preservation revealed details colonial records had never captured. Earlier Dutch accounts often portrayed the Tambora kingdom as remote and relatively insignificant, yet the recovered artifacts suggested a far more sophisticated society. The craftsmanship of metalwork, the organization of domestic spaces, and the variety of cultural objects indicated a complex civilization with trade connections, skilled artisans, and established social structures. Because the Tambora people left no surviving written records and no direct descendants speaking their language, nearly everything known about them must now be reconstructed through physical evidence recovered from beneath the ash. Each object excavated from the buried village carries unusual weight. A cooking vessel becomes proof of daily routine. A bronze bell becomes evidence of ceremony, craftsmanship, and belief. For 189 years, the kingdom remained sealed beneath volcanic deposits while forests grew overhead and generations passed beyond memory of the people below. Then, slowly, the mountain began releasing fragments of the world it had preserved. The lost civilization of Tambora had not vanished entirely. It had been waiting in darkness beneath the ash, held in suspension by the same eruption that destroyed it. Long before the eruption, conversations moved across the slopes of Tambora in sounds no longer heard anywhere on Earth. Parents spoke to children beside cooking fires. Traders negotiated in village markets. Songs, stories, prayers, jokes, and royal ceremonies unfolded in a language carried through generations entirely by living voices. Then, within the span of a single night, in April of 1815, those voices disappeared. Among the most haunting consequences of Tambora's eruption is not geological but linguistic. The people living on the mountain spoke a language unlike any other known language in the Indonesian archipelago. Linguists classify it as a language isolate, meaning it possessed no confirmed relatives and belonged to no recognized language family. Most languages exist within larger, connected groups shaped by shared ancestry across centuries. Tambora's language appears to have stood alone. When every speaker died during the eruption, the language itself died with them. This was not the fading of a regional accent or the gradual replacement of one dialect by another. It was the complete extinction of an entire branch of human expression. A distinct system for describing reality vanished permanently because no surviving community remained to carry its words into the future. Only fragments survive now. Before the eruption, Dutch colonial administrators recorded a small number of Tambora words and phrases during brief contact with the kingdom. The surviving vocabulary is extremely limited, consisting mostly of isolated terms preserved in scattered documents. There is enough evidence for linguists to confirm that the language differed substantially from neighboring tongues, yet nowhere near enough material exists to reconstruct its grammar, literature, or full sound system. The result is an unusual silence within linguistic history. Scholars know the language existed. They know approximately when and why it vanished. Yet they cannot recover the inner structure of the world it once described. Every language carries its own framework for organizing experience. Linguists, studying endangered languages, often describe them as unique maps of human thought. Vocabulary reflects environmental knowledge, social relationships, memory, ritual, humor, and perception accumulated across generations. Some languages classify color differently. Others divide time, landscape, or emotion according to concepts difficult to translate directly into another tongue. The Tambora language contained its own ways of naming seasons, describing the mountain, explaining kinship, and understanding the surrounding world. Those patterns of thought disappeared when the final speakers died beneath ash and pyroclastic flows on the night of April 10th. Unlike many ancient lost languages, Tambora's extinction can be tied to a single identifiable event. Most vanished languages fade gradually through migration, conquest, assimilation, or cultural change unfolding across centuries. Tambora's language ended almost instantaneously, erased alongside the civilization that sustained it. This makes the eruption one of the most complete acts of cultural erasure recorded in human history. A kingdom disappeared, a royal lineage vanished, oral traditions accumulated through generations dissolved without written preservation. Stories once spoken aloud across villages on Sumbawa no longer exist in any recoverable form. Today, only scattered archaeological remains and a few recorded words remain to suggest the intellectual world that once flourished there. The mountain destroyed not only bodies and buildings, but an entire way of understanding reality. Somewhere within the lost language of Tambora were metaphors, songs, and ideas that no human mind will ever encounter again, because the last people who carried them vanished in a single night beneath the eruption. When the ash finally began settling back toward the earth, the shape of Tambora itself had changed beyond recognition. Sailors approaching Sumbawa from the sea no longer saw the towering volcanic cone that had dominated the horizon for countless generations. The summit that once rose more than 14,000 feet into the humid air of the Indonesian archipelago had vanished. Nearly 4,000 feet of mountain had been erased during the eruption, blasted outward into the atmosphere, and scattered across ocean, island, and sky. What remained looked less like a peak than a wound in the crust of the earth. At the center of the ruined volcano lay an immense caldera, a bowl-shaped depression approximately 3.7 miles across and more than 2,000 feet deep. Its walls were steep and unstable, layered with fractured rock still stained in pale shades of gray and brown. During the rainy seasons that followed, water slowly gathered along the basin floor, forming a crater lake beneath the shattered rim. Mist drifted across the hollow during the early mornings, softening the violence recorded in the stone itself. For miles in every direction, the surrounding landscape appeared stripped of life. Thick blankets of ash and pumice covered valleys, forests, and former farmland. Trees that had survived the initial catastrophe stood leafless and blackened, their trunks buried halfway in volcanic debris. Rivers carried fine sediment down the slopes, turning the water heavy and opaque. During rainfall, the absence of roots holding the earth together caused enormous landslides to slide down the mountain's flanks, exposing fresh scars across the unstable terrain. Entire sections of hillside moved slowly downward under their own weight, reshaping the island long after the eruption had ended. Yet, even in that damaged silence, recovery began almost immediately, though at a pace nearly invisible to human lives. Wind carried spores and seeds onto the sterile ground. Hardy grasses and small pioneering plants appeared first, threading themselves through cracks in the ash. Ferns followed in damp ravines where moisture collected. Over years, then decades, the slow chemistry of decay and rainfall transformed volcanic deposits into new soil. Forests eventually returned in scattered patches, though the mature ecosystems that once surrounded Tambora required generations to rebuild themselves. The human recovery moved even more slowly. Sumbawa's economy had depended heavily upon the fertile volcanic earth surrounding the mountain, and much of that agricultural foundation had been buried beneath layers of ash too deep for immediate cultivation. Villages that escaped direct destruction struggled with famine, displacement, and isolation. Dutch colonial administrators attempted to encourage resettlement across the devastated region, but many survivors resisted returning to landscapes associated with loss and suffering. Some communities abandoned the area entirely, leaving former roads and fields to disappear beneath vegetation and erosion. Today, Tambora remains active, though quiet. Its vast caldera can be seen clearly from orbit, a circular mark pressed into the island of Sumbawa and visible from satellite imagery high above Southeast Asia. Forests now cover much of the volcano once more, and the mountain has become part of an Indonesian national park. Yet beneath the green canopy and drifting clouds, the altered shape of Tambora still preserves the memory of the night the mountain tore itself apart. Long after the skies cleared and the failed harvests passed into memory, scientists searching for ways to compare volcanic eruptions faced a difficult problem. Volcanoes do not behave like earthquakes or storms. Some produce slow rivers of lava that advance quietly across the land. Others release towering clouds of ash, gas, and shattered stone capable of altering climates far beyond the horizon. Measuring the true scale of such events required a language of magnitude broad enough to describe forces that reshaped continents and civilizations alike. Modern volcanology eventually developed the Volcanic Explosivity Index, commonly called the VEI. The scale begins at 0 and rises to 8, with each increase representing roughly 10 times more erupted material than the level before it. A VE1 eruption may send ash drifting above a local landscape for a short time. By the upper numbers, entire planetary systems begin to respond. The scale is logarithmic, quiet at the beginning, then rapidly enormous. When Mount St. Helens erupted in 1980, collapsing its northern flank and covering parts of Washington state in ash, it measured a VEI 5. The eruption became one of the defining volcanic disasters of the modern era, captured by cameras and satellites in extraordinary detail. 11 years later, Mount Pinatubo in the Philippines erupted with far greater force. Pinatubo reached VEI 6, injecting enough sulfur into the atmosphere to cool global temperatures measurably for several years afterward. Sunsets brightened around the world, and climatologists tracked the subtle decline in average planetary warmth with modern instruments and atmospheric models. Tambora stood another full step above even that event. Its eruption in 1815 measured VEI 7, placing it among the largest eruptions of the last 10,000 years. Only one other confirmed eruption in recorded human history has reached the same classification: the eruption of Rinjani in the year 1257 on the neighboring island of Lombok. Ice core records from Greenland and Antarctica preserve traces of that medieval eruption in layers of sulfate trapped within ancient snow. Historians now suspect it contributed to years of unusual weather and famine across parts of Europe, though the written records remain fragmented and incomplete compared with the immense documentation surrounding Tambora. Above VEI 7 lies a category that human civilization has never directly witnessed. A VEI 8 eruption, often described as a supervolcano event, represents another tenfold increase in eruptive power. The most recent known example occurred approximately 74,000 years ago at Toba in present-day Sumatra. Geological evidence suggests the eruption released extraordinary volumes of ash and sulfur into the atmosphere, darkening skies across large parts of the planet. Some researchers believe the resulting climatic disruption reduced the total human population to only a few thousand surviving individuals scattered across isolated regions. Tambora, immense as it was, released roughly one-tenth the eruptive material estimated for Toba. Yet even at that lower magnitude, the eruption disrupted harvests across continents, altered weather systems, spread disease, and contributed to the deaths of potentially hundreds of thousands of people. For volcanologists, Tambora became a living scale model for something even larger, a reminder that the deepest forces beneath the earth do not recognize the boundaries of nations or generations. Deep beneath volcanic regions across the planet, magma chambers continue their slow movement through fractured rock, gathering pressure over spans of time far longer than human governments or civilizations endure. Modern volcanologists do not view eruptions like Tambora as impossible anomalies sealed safely in the past. Geological records preserved in ash layers, ice cores, and ancient sediments show that eruptions on the scale of VEI 7 occur repeatedly across Earth's history, often separated by centuries of quiet that make them easy for societies to forget. In 1815, the world held roughly 1 billion people. Most communities depended directly on nearby harvests, and transportation between continents moved at the pace of sail and horse. Today, the global population has grown beyond 8 billion, connected through trade systems so tightly interwoven that food harvested on one continent may be consumed on another within weeks. Modern agriculture appears vast and technologically sophisticated, yet its stability depends upon remarkably delicate timing. Seasons must remain predictable enough for planting schedules, rainfall patterns, fertilizer transport, refrigeration networks, and shipping lanes to function together without interruption. A Tambora-scale eruption in the modern world would not remain a regional disaster for long. Climate models suggest that a massive injection of sulfur dioxide into the stratosphere would once again create a global aerosol veil, reducing incoming sunlight and cooling surface temperatures across large portions of the planet. A study published in 2019 estimated that an eruption comparable to Tambora could reduce worldwide crop production by roughly 10 to 15% during the first year alone. That decline might appear modest when expressed numerically, yet modern civilization operates on extraordinarily narrow margins between production and consumption. Most major cities maintain only a few days of food within local storage systems at any given moment. Supermarkets appear abundant because transportation networks replenish them continuously. Grain reserves stored globally provide a slightly larger buffer, though current estimates place that reserve at approximately 77 days of world food supply. A prolonged agricultural disruption lasting several growing seasons, similar to the conditions that followed 1816, could begin exhausting those reserves within months. Regions already vulnerable to drought, conflict, or economic instability would likely experience severe shortages first, though the interconnected nature of global trade means no nation would remain entirely insulated. The effects would move through financial systems as quietly as ash spreading through the upper atmosphere. Crop failures in multiple regions would raise food prices worldwide. Governments might restrict exports to protect domestic supplies, placing additional strain on importing nations. Livestock industries would struggle as feed costs increased. Shipping delays, energy demands, and labor disruptions would ripple outward across economies already dependent on constant coordination between continents. Modern infrastructure, despite its sophistication, has rarely been tested against a simultaneous climatic shock affecting nearly every agricultural region in the Northern Hemisphere at once. Yet the modern world also possesses something absent in 1815. Satellites monitor volcanic activity continuously. Atmospheric scientists can model aerosol dispersal within hours of a major eruption. International communication systems allow warnings, forecasts, and scientific data to move instantly around the globe. Humanity now understands the mechanism of volcanic winter with extraordinary detail. The uncertainty lies not in whether the science is visible, but whether civilizations built around constant growth and uninterrupted supply could adapt quickly enough when the sky itself begins filtering sunlight away from the surface of the earth. Across the planet, beneath mountain ranges, island arcs, and ancient calderas softened by forests and snow, magma continues to move through the crust in slow and silent currents. Most volcanic systems remain quiet for spans of time, so immense that entire civilizations rise and disappear between eruptions. Human memory struggles against geological patience. A volcano inactive for centuries can appear permanent and settled, even while pressure steadily accumulates far below the surface. In the western United States, the Yellowstone volcanic system rests beneath a broad plateau of rivers, forests, and geothermal springs. Beneath that landscape lies one of the largest known magma reservoirs on Earth. Its last major eruption occurred approximately 640,000 years ago and reached VEI 8, ejecting enough material to blanket huge portions of North America in ash. The caldera itself stretches across dozens of miles, though visitors standing beside its lakes and steaming vents rarely perceive the immense structure beneath them. Seismometers and ground deformation instruments continuously monitor the region now, tracking subtle movements within the crust that might once have passed unnoticed. Far across the Atlantic, another volcanic system has been drawing scientific attention in southern Italy. Campi Flegrei, near Naples, is not dominated by a single towering cone, but by a broad volcanic field containing craters, fumaroles, and densely populated neighborhoods. Since 2012, the region has shown signs of increasing unrest. The ground has been rising gradually through a process known as bradyseism, caused by pressure changes beneath the surface. Swarms of small earthquakes ripple through the area periodically, while volcanic gases seep upward through cracks in the earth. Millions of people live within reach of the system, creating a situation where scientific observation and human geography exist in constant tension. Along the Indonesian archipelago, the same tectonic forces that created Tambora continue shaping the islands today. Indonesia sits directly on the Pacific Ring of Fire, the vast horseshoe-shaped zone where multiple tectonic plates collide and descend beneath one another. Approximately 130 active volcanoes rise across the nation, more than any other country on Earth. In 2017, Mount Agung on Bali erupted after decades of relative quiet, forcing the evacuation of roughly 100,000 people. Ash drifted into the atmosphere above airports and villages, while monitoring stations tracked the volcano's behavior hour by hour. Unlike the world of 1815, modern volcanology possesses extraordinary tools for observing these systems. Satellites detect subtle thermal changes across volcanic slopes. GPS instruments measure ground deformation down to centimeters, revealing the inflation of magma chambers months or even years before eruption. Gas spectrometers analyze sulfur dioxide and carbon emissions escaping from vents, helping scientists estimate changes occurring underground. Combined with seismic monitoring, these technologies have transformed eruptions from sudden mysteries into processes that can often be observed developing in real time. Those warnings have already saved many lives. During the 1991 eruption of Mount Pinatubo in the Philippines, scientists accurately forecast the eruption with enough precision to evacuate tens of thousands of people before the climactic explosion. Yet, even with modern knowledge, the challenge remains immense. Evacuating entire cities based on probabilistic forecasts requires political trust, infrastructure, resources, and public cooperation on a scale few societies sustain easily for long periods. Tambora remains part of that conversation now, not as a distant historical curiosity, but as a reminder that the earth beneath modern civilization is still alive, still shifting quietly beneath the structures humans build above it. In libraries across Europe and North America, the year 1816 survives in letters, weather journals, paintings, and literary history. Historians describe darkened skies over Switzerland, failed harvests in New England, and cold rain falling over English fields during midsummer. The eruption of Tambora often enters these narratives indirectly, appearing as the distant cause behind famine, strange sunsets, or the writing of Frankenstein. Yet, thousands of miles from those preserved documents and celebrated cultural memories lay the island where the eruption actually occurred, where entire communities disappeared so completely that many of their names faded from history itself. Approximately 71,000 people are believed to have died in Indonesia as a result of the eruption and its aftermath. Many perished during the immediate catastrophe, while others died from starvation, disease, or displacement in the months that followed. Their deaths unfolded within a colonial world where indigenous suffering was rarely documented with the same detail granted to European experiences. The surviving written accounts came largely from Dutch colonial officials whose reports focused on damaged trade routes, disrupted agriculture, and the administrative consequences of regional collapse. Human lives entered those records unevenly, often reduced to numbers attached to economic losses. The civilizations destroyed on Sumbawa existed mostly beyond the written traditions recognized by European empires. The Kingdom of Tambora and the Kingdom of Peket maintained their own cultures, languages, political systems, and oral histories, yet almost none of that internal world survived the eruption. What remains today comes filtered through colonial descriptions written by outsiders who observed these societies briefly and imperfectly before they vanished. The imbalance creates a strange distortion in historical memory. European accounts preserve the cold summer that followed the eruption with vivid detail, while the destruction of the communities closest to the volcano often occupies only a few paragraphs in the broader story. This uneven remembrance reflects patterns repeated throughout colonial history. Natural disasters affecting colonized populations were frequently treated as distant background events unless their consequences reached European economies or cultural life. The failed harvests of Europe became major historical themes. The vanished Indonesian kingdoms became fragments scattered through administrative reports and shipping records. Entire peoples disappeared into silence, while the atmospheric effects drifting over Europe entered poetry, art, and scientific discussion. In recent decades, historians, archaeologists, and linguists have begun working carefully against that silence. Excavations on the slopes of Tambora seek not only geological evidence, but traces of the people who once lived there. Ceramic vessels, tools, food remains, and household objects recovered from beneath volcanic ash provide glimpses into a civilization erased before most of the world even knew it existed. The excavation begun in 2004 marked one of the first serious attempts to place the people of Tambora themselves at the center of the story rather than at its margins. Their absence remains difficult to fully comprehend. No surviving chronicles describe the final hours from within the kingdom. No descendants preserve its language in living memory. What endured instead were distant accounts written by those who observed the aftermath from safer shores. Slowly, through archaeology and historical reconstruction, fragments of that lost world are being gathered again. The story of Tambora is not only about climate, geology, or global catastrophe. It is also about remembering the people nearest to the mountain, whose lives disappeared first and whose history waited the longest to be heard. Morning returned slowly to Sumbawa after the eruption, though in many places the sun arrived only as a dim pale glow through suspended ash. Along the coastlines and inland valleys, people emerged from shelters, ruined homes, and temporary camps into landscapes that no longer resembled the island they had known. Approximately 50,000 people survived the first violence of the eruption, yet survival carried them into another kind of catastrophe, quieter and longer lasting, unfolding day by day beneath a sky still stained with volcanic dust. The land itself had become hostile to ordinary life. Fields that once supported rice, maize, and root crops vanished beneath layers of ash several feet deep. The volcanic deposits hardened under tropical rain into heavy crusts that roots could not penetrate. Irrigation systems disappeared. Fruit trees stood leafless and gray. Livestock wandered through empty terrain, searching for food that no longer existed. For farming communities whose lives moved with seasonal planting cycles, the destruction of arable land meant the collapse of stability itself. Hunger arrived gradually, then, all at once. Freshwater sources became another source of danger. Rivers and wells filled with ash and acidic runoff from the mountain. During rainfall, dark sediment washed continuously from the devastated slopes into streams below. Survivors drank contaminated water because no alternatives remained. Illness spread rapidly through weakened populations, already suffering from burns, respiratory injuries, and malnutrition. Fever and dehydration moved through crowded settlements, where displaced families gathered together beneath temporary shelters made from salvaged wood and woven mats coated in ash. Dutch colonial authorities attempted to organize relief shipments from neighboring islands, but the scale of destruction exceeded anything their regional administration had previously encountered. Food supplies moved slowly across damaged ports and hazardous waters, still carrying floating pumice. Some survivors received rice or dried provisions. Others received nothing for weeks. Colonial officials also began relocating communities away from the worst affected regions of Sumbawa. In many cases, these relocations were compulsory, separating people from ancestral land, burial grounds, and surviving relatives. Villages that had existed for generations dissolved into scattered populations dispersed across unfamiliar coastlines and neighboring islands. The rupture extended beyond physical survival. Community structures weakened as displacement interrupted traditions tied to specific landscapes and sacred sites around the mountain. Ceremonies connected to planting seasons disappeared. Oral histories lost elders who had preserved them. Families fragmented under the pressure of famine, disease, and forced movement. The eruption had already erased kingdoms in a single night. Now the long aftermath slowly unraveled the social fabric of the people who remained. Yet memory endured in quieter forms. During the 20th century, researchers collecting oral traditions from Sumbawa communities encountered stories passed carefully across 7 generations. Elders described mountains that exploded with fire, seas disturbed by unnatural waves, darkness that lasted for days, and villages swallowed beneath ash. The details shifted across time, yet the emotional shape of the event remained embedded within collective memory, carried through songs, warnings, and ancestral storytelling long after written records faded. Recovery came slowly. Historians estimate that Sumbawa's population required nearly 50 years to return to pre-eruption levels. Forests eventually returned to the mountain slopes, and settlements rose again along the coast. But the world rebuilt by the survivors differed profoundly from the one that existed before April 1815. The mountain remained, altered beyond recognition, towering above communities that continued living in the shadow of an absence that could never fully be restored. Far from Indonesia, beyond shipping routes and ruined coastlines, another archive was quietly recording the eruption in perfect silence. Snow continued falling across Greenland and Antarctica during the years after 1815, settling into thin annual layers that compressed slowly into ice. No human witness observed the process. No chronicler wrote about it. Yet within those frozen sheets, the atmosphere of the planet preserved itself with extraordinary precision, sealing away traces of Tambora long after survivors and empires had vanished. Modern scientists reach these records by drilling deep into polar ice caps and extracting narrow cylinders called ice cores. Each core contains stacked layers formed year after year, extending backward through centuries and, in some places, hundreds of thousands of years. The deeper the drill descends, the further backward in time the record travels. Tiny air bubbles, trapped within the ice, preserve samples of ancient atmospheres. Dust settles into visible bands. Chemical residues from fires, storms, industrial pollution, and volcanic eruptions remain suspended exactly where they fell. When researchers analyzed the layer corresponding to 1815, they found an unmistakable signal. Greenland ice cores contained a sharp spike in sulfate concentration, far larger than surrounding years. The sulfur dioxide injected into the stratosphere by Tambora had eventually transformed into sulfate aerosols, drifted around the globe, and settled gradually onto the polar ice. What had once darkened skies over Sumbawa and cooled continents now appeared as a thin chemical trace trapped beneath miles of frozen water. The signal was so clear that it became a chronological anchor for climate science. Ice core researchers use the Tambora sulfate spike as a fixed timestamp when calibrating other sections of the polar record. In a landscape where years blur into pale, compressed layers, the eruption stands out like a bright marker line across the history of the atmosphere. The planet itself had recorded the event with remarkable consistency. Even more striking was the discovery that Antarctic cores contained the same sulfate layer. Tambora's aerosols had crossed the equator and reached both poles, confirming the truly global scale of the eruption. Winds in the stratosphere carried volcanic particles across hemispheres and oceans, wrapping the Earth in a veil whose remnants eventually settled onto snowfields thousands of miles from the volcano itself. The ice revealed the scale of circulation in a way no 19th century observer could have understood. The frozen record also suggested that Tambora was not acting alone. Layers immediately before and after 1815 showed evidence of additional volcanic activity, including a major eruption in 1809 whose source volcano remains unidentified. Scientists now believe this earlier eruption may have already cooled the climate slightly before Tambora erupted. The combined atmospheric effects of multiple eruptions could explain why the volcanic winter of 1816 became so unusually severe across the northern hemisphere. Other clues emerged from the same layers. Ice cores from this period preserve subtle evidence of reduced carbon dioxide absorption by vegetation worldwide, consistent with failed harvests, damaged forests, and widespread ecological stress. Even the response of plant life became encoded into the chemistry of the ice. The remarkable thing about polar ice is not simply that it preserves history, but that it preserves it continuously. Storms disappear, kingdoms collapse, languages fade, yet the frozen layers remain undisturbed beneath the poles, storing atmospheric memories with patient accuracy. More than 2 centuries after Tambora erupted, the mountain still exists inside the ice, waiting in silence beneath Antarctica and Greenland, written there in sulfur and snow. Long before satellites, radio transmissions, or global communication networks, the eruption announced itself to the planet through pressure and sound. Across thousands of miles of ocean, people heard Tambora without knowing what they were hearing. The atmosphere itself carried the message outward in expanding waves, rolling through clouds, coastlines, forests, and harbors with a force almost impossible to comprehend. In an age when most human beings would never travel beyond their own region, the mountain briefly connected distant civilizations through a single shared noise. The climactic explosion released one of the greatest bursts of acoustic energy produced by any natural event in recorded history. On the island of Sumatra, approximately 1,600 miles from Tambora, witnesses reported hearing deep booming sounds that seemed to come from the horizon itself. Similar reports emerged from Timor to the east. At such enormous distances, the eruption no longer sounded like a nearby detonation. The sharp violence of the blast had stretched and softened across the atmosphere into slow, rolling concussions, like distant artillery echoing over water. In Batavia, the colonial capital now known as Jakarta, British soldiers stationed at the garrison believed enemy ships were exchanging cannon fire offshore. Officers organized patrols and prepared responses to what they assumed was a naval conflict somewhere beyond the harbor. The sounds continued intermittently, arriving through the humid air with enough clarity to convince experienced military personnel that warfare was unfolding nearby. Only later did officials realize the source lay hundreds of miles away on a volcanic island many of them had barely considered significant. The eruption moved not only through the air, but through the ground itself. Pressure waves passed into surrounding landmasses and oceans, creating vibrations detectable even by the limited scientific instruments available during the early 19th century. Primitive seismometers recorded disturbances without fully understanding their origin. The planet had reacted as a connected physical system, carrying the energy of the explosion outward through rock, sea, and atmosphere simultaneously. Beyond the range of ordinary human hearing, Tambora also generated immense infrasound, frequencies so low they are perceived more as pressure than sound. These waves traveled extraordinary distances through the upper atmosphere with little loss of energy. Modern scientists studying nuclear test detection systems have retrospectively modeled the eruption and concluded that the atmospheric pulse circled the globe multiple times. Weather stations in Europe recorded unusual fluctuations in barometric pressure as the wave passed overhead, though observers at the time could not possibly have known they were measuring the aftermath of a volcanic explosion on the far side of the world. The estimated acoustic energy released by Tambora exceeded the Hiroshima atomic bomb by roughly 10,000 times. Yet, unlike a weapon designed and controlled by human beings, the eruption emerged from geological forces operating deep beneath Earth's crust, driven by pressure accumulated over centuries in silence beneath the island. For a few terrible hours, the atmosphere became a medium, carrying that buried energy across the entire planet. What remains remarkable is how many people encountered the eruption only as sound. Sailors paused on dark seas, listening to distant thunder beneath clear skies. Soldiers searched empty horizons for invisible fleets. Villagers woke during the night to vibrations passing through wooden walls and stone foundations. Even those who never saw ash or darkness still heard the mountain in some form, audible or inaudible, as the atmosphere carried Tambora's voice around the world and slowly let it fade into silence. By the time modern climate science emerged in the 20th century, Tambora had already become more than a historical eruption. It had transformed into a planetary case study, preserved not only in journals and ice cores but in temperature records, tree rings, agricultural archives, and atmospheric chemistry. Few events in recorded history produced such a clear demonstration of how deeply the atmosphere shapes human civilization. The eruption became, in effect, a vast natural experiment conducted by the Earth itself. Climate scientists study Tambora because it provides something exceedingly rare in planetary science, a measurable example of sudden global cooling caused by a known atmospheric mechanism. The eruption injected enormous quantities of sulfur dioxide into the stratosphere, where the gas converted into sulfate aerosols that reflected sunlight away from Earth's surface. Modern computer models now simulate this process in detail, comparing atmospheric circulation patterns, temperature shifts, crop failures, and precipitation anomalies against historical observations from the years following 1815. Again and again, the records align: the dimmed sunlight, the colder summers, the disrupted monsoons, the failed harvests spread across continents. Tambora demonstrated that relatively small changes in incoming solar radiation could destabilize food systems and weather patterns on a planetary scale. The atmosphere, once imagined as a passive background to human history, revealed itself as an active and fragile system linking oceans, crops, storms, economies, and survival itself. This understanding eventually shaped scientific thinking far beyond volcanology. During the Cold War, researchers studying the potential aftermath of nuclear war began examining Tambora closely. They realized that large-scale firestorms from nuclear explosions could loft smoke and soot high into the atmosphere, producing cooling effects similar to volcanic aerosols. The same physical principles applied. Sunlight blocked in the upper atmosphere would reduce surface temperatures and shorten growing seasons. Modern nuclear winter models trace part of their intellectual foundation directly to observations gathered from the years after Tambora erupted. The implications were unsettling. Scientists concluded that famine caused by atmospheric cooling might kill more people than the explosions themselves. Once again, Tambora served as evidence that disruptions to sunlight and climate ripple outward through agriculture with extraordinary speed. The eruption became a warning encoded in historical data, showing how dependent civilization remains on stable seasons and predictable harvests. In recent decades, Tambora has entered another scientific debate, this time surrounding solar geoengineering. Some researchers have proposed deliberately injecting sulfate aerosols into the stratosphere to reduce global warming by reflecting a portion of incoming sunlight back into space. Supporters point to volcanic eruptions as proof that the mechanism works. After Tambora, the planet cooled measurably and quickly. Nature had already performed the experiment. Yet Tambora also exposed the dangers. The cooling was uneven across regions. Rainfall patterns shifted unpredictably. Agriculture suffered severe disruption. Entire populations experienced famine and disease because atmospheric changes do not distribute themselves gently or equally. Critics of geoengineering argue that Tambora revealed how difficult it would be to manage such interventions safely on a planetary scale. For this reason, scientists studying the eruption are not only reconstructing the past, they are evaluating futures that humanity may confront within decades. The sulfur trapped in polar ice, the failed harvests recorded in village archives, the altered skies painted across 19th century canvases, all now inform discussions about climate intervention, global risk, and technological power. Tambora remains present inside modern science because the questions it raised never truly ended. A mountain capable of darkening skies across the world feels immense when measured against a human lifetime. Tambora erased kingdoms, altered climates, disrupted harvests across continents, and entered the memory of entire civilizations. Yet, beneath the perspective of deep geological time, the eruption occupies only a small place in a far older pattern, one written not in years or centuries, but in epochs stretching across hundreds of millions of years. The Earth has produced volcanic events vastly larger than Tambora, many times before human beings existed. Across the geological record lie traces of eruptions so prolonged and immense that they reshaped oceans, atmospheres, and the trajectory of evolution itself. Modern volcanologists study these ancient episodes through buried lava provinces, isotope chemistry, extinction layers, and fossil collapse horizons preserved within rock strata around the world. Approximately 66 million years ago, near the end of the age of dinosaurs, enormous fissures opened across what is now India. Lava poured continuously onto the surface in eruptions now known as the Deccan Traps. Rather than a single explosion, the event unfolded through repeated outpourings over hundreds of thousands of years. Layer upon layer of basalt spread outward until the volcanic province covered an area comparable to modern India itself. The atmosphere filled repeatedly with volcanic gases and aerosols, while ecosystems struggled beneath prolonged environmental stress. The eruptions occurred at nearly the same time as the asteroid impact associated with the extinction of the non-avian dinosaurs, and many scientists now believe the two disasters interacted together in destabilizing Earth's climate and biosphere. Even deeper in time lies an event more devastating still. Around 252 million years ago, vast eruptions across Siberia produced lava flows on a scale almost beyond imagination. The Siberian traps released extraordinary quantities of carbon dioxide, sulfur compounds, and methane, triggering extreme climate disruption, ocean acidification, and oxygen collapse in marine environments. The result was the Permian extinction, the largest mass extinction known in Earth's history. Approximately 96% of marine species disappeared. Forest ecosystems collapsed. Entire branches of life vanished permanently from the planet. These were not isolated explosions, separated neatly from ordinary time. They were sustained volcanic intervals lasting thousands to hundreds of thousands of years, periods when the Earth itself seemed to enter prolonged instability. Compared beside such events, Tambora becomes something smaller, though no less real to the people who endured it. It was a single eruption within a planet that has repeatedly transformed itself through forces operating deep beneath the crust. This perspective changes the meaning of volcanic quiet. Human civilization developed during an unusually stable interval in Earth's geological history. Agriculture, cities, global trade, written language, and industrial society all emerged during a period lacking any confirmed VEI 8 eruption. The atmosphere remained comparatively predictable. Seasons stabilized enough for civilizations to depend upon them generation after generation. Yet the geological record suggests stability is not permanence. The Earth is not a passive surface supporting life from beneath. It is an active system of shifting plates, rising magma, circulating oceans, and changing atmospheres. Over immense spans of time, those systems repeatedly alter the conditions under which life exists. Tambora reminds modern humanity that even catastrophic events can represent only brief moments within that much larger planetary rhythm. Beneath forests, oceans, and cities, the deeper conversation of the Earth continues slowly and without pause, moving according to timescales far older than memory. There are moments in Earth's history when cause and consequence spread outward so widely that the boundaries between geology and human civilization begin to disappear. Tambora was one of those moments. A single eruption on a remote Indonesian island rippled through climate systems, migration patterns, literature, disease, ecology, technology, agriculture, and memory with a reach so broad that even now it feels difficult to hold entirely in the mind at once. One volcano erupted during the night of April 1815. The immediate death toll reached approximately 71,000 people, though modern estimates suggest the famine and disease that followed may have carried the total closer to 1 million across multiple continents. Entire villages vanished beneath ash and pyroclastic flows. A kingdom disappeared so completely that archaeologists would spend centuries searching for traces of its existence beneath hardened volcanic deposits. A language isolate, spoken nowhere else on Earth, ceased to exist in a single night when every fluent speaker died together on the mountain's slopes. Beyond Indonesia, the consequences continued unfolding quietly through atmosphere and weather. Crops failed across Europe, North America, and Asia. Families who had never heard the name Tambora experienced freezing summers, relentless rain, drought, famine, and soaring food prices because sunlight itself had changed. Rivers flooded unexpectedly. Harvest calendars failed. Communities that had depended on stable seasons for generations suddenly found those patterns broken. The disruptions reached into disease as well. Altered monsoon systems and widespread malnutrition helped create conditions linked to the first global cholera pandemic, a wave of infection that would reshape 19th century public health and eventually spread across much of the world. At nearly the same time, another chain of consequences unfolded through transportation and invention. Horse populations collapsed under the pressure of failed harvests and expensive feed. In Germany, Karl von Drais responded to the shortage by developing the Laufmaschine, the ancestor of the modern bicycle. Even art and literature bent subtly beneath the altered skies. The cold storm-filled summer beside Lake Geneva confined a group of writers indoors, where Mary Shelley imagined Frankenstein. Lord Byron wrote darkness beneath volcanic sunsets and dimmed European skies. Painters across the Romantic period began capturing strange oranges, reds, and prolonged twilight effects produced by sulfate aerosols suspended high in the atmosphere. 2 years of altered sunsets entered the visual language of an entire artistic generation. Science changed as well. Tambora forced early meteorologists, climatologists, and volcanologists to recognize that Earth's atmosphere operates as a connected global system. Observers began comparing weather records across countries. Scientists studying the eruption centuries later would use it to understand nuclear winter, aerosol cooling, and planetary climate feedbacks. The event became a foundational reference point for modern climate science itself. Yet, despite all of this, Tambora remains strangely absent from public memory. Many people alive today have never heard of the mountain. Sumbawa rarely appears in global history surveys. The eruption often survives only as a brief mention between discussions of Napoleon and industrialization, reduced to a historical curiosity called the Year Without a Summer. But Tambora reveals something profound about the relationship between humanity and the natural world. Civilization often imagines itself moving according to politics, economies, inventions, and wars. Beneath those stories, the Earth continues operating according to systems vastly older and larger than human attention. Occasionally, for a brief moment, those deeper systems rise to the surface and rearrange history all at once. Long after the ash settled and the skies cleared, another silence remained behind, quieter than the eruption itself. It existed in archives, in museums, in the uneven distribution of memory. Some lives from 1815 survived in letters, paintings, journals, and published books. Others survived only as fragments beneath volcanic stone, waiting in darkness for strangers, centuries later, to uncover them carefully with brushes and small metal tools. The imbalance is difficult to ignore once it becomes visible. European farmers who endured the cold summers of 1816 left diaries describing ruined crops and strange weather. Wealthy travelers wrote about crimson sunsets above distant lakes. Famous poets transformed the dimmed atmosphere into literature studied around the world. Mary Shelley's name endured across 2 centuries, carried through libraries, classrooms, films, and conversation. Yet the people who died closest to the mountain remain largely anonymous, despite carrying the full physical force of the disaster itself. 2 skeletons discovered beneath the ash in 2004 still have no names. Archaeologists found them inside a buried structure, preserved where death reached them instantly. Nearby sat bronze vessels, ceramic containers, tools arranged as though work had only briefly paused. These objects revealed craftsmanship, trade, hierarchy, and daily ritual. They belonged to a civilization sophisticated enough to sustain courts, artisans, and distinct cultural traditions, yet history recorded almost none of its inner life. Part of this absence comes from the nature of colonial history itself. The surviving written records describing Tambora were produced mainly by Dutch administrators whose priorities centered on trade routes, taxation, shipping, disruption, and regional governance. Indigenous kingdoms entered those records only when their existence intersected with colonial administration. Entire populations could disappear and remain visible in official documents merely as lost labor, interrupted commerce, or declining agricultural output. History often follows the path of preserved paper. Literate empires leave behind archives heavy enough to anchor memory across centuries. Oral cultures remain more vulnerable to catastrophe because their histories live within people rather than libraries. When Tambora erased villages, families, and language speakers, it also erased songs, genealogies, myths, place names, ceremonies, and ways of understanding the world that had never been written down. The destruction moved beyond physical death into cultural disappearance. Modern archaeology on Sumbawa has begun pushing gently against that disappearance. Each recovered artifact shifts attention back toward the people nearest the eruption rather than those who later interpreted it from distant continents. A bronze bell lifted from volcanic soil carries a different emotional weight than a European newspaper article describing unusual weather. One object speaks from inside the catastrophe itself. Nothing uncovered from beneath the ash can fully restore what vanished there. The Tambora language remains unrecoverable except for a few surviving words copied by outsiders before the eruption. Royal lineages dissolved without descendants able to preserve them. Personal names disappeared alongside the voices that once spoke them aloud. The gaps cannot be repaired completely because too much was lost too quickly. Yet, remembrance still matters, even when incomplete. Attention changes the shape of history. To place the people of Tambora at the center of this story is not simply an academic correction. It is an acknowledgement that the lives buried beneath the mountain were not background figures in a global climate event. They were the first human world the eruption touched, and the one that paid the highest price when the earth shifted beneath them. Across the northern coast of Sumbawa, Tambora now rises in silence beneath drifting clouds and tropical rain, its slopes covered once more in forest. From a distance, the mountain appears calm, almost softened by time. Birds move through the canopy. Mist gathers along the ridges at dawn. The vast wound, left by the eruption of 1815, has become part of the landscape itself, folded into maps, satellite images, and the routines of villages built in the shadow of the caldera. Yet the stillness is not the stillness of something finished. Tambora remains an active volcano. Smaller eruptions have occurred repeatedly since the catastrophe that altered the 19th century, reminders that the systems beneath the mountain never fully stopped moving. Increased seismic activity, recorded in 2011 and 2013, drew renewed attention from Indonesian volcanological authorities, who maintain continuous monitoring networks around the volcano. Seismometers listen for subtle fractures deep underground. GPS instruments measure changes in the shape of the mountain so small they would otherwise pass unnoticed. Gas emissions are sampled and compared over time, each measurement part of an ongoing conversation between scientists and the earth beneath their feet. Far below the crater lake resting inside the caldera, magma continues to accumulate slowly within chambers shaped by ancient eruptions. The mountain that lost thousands of feet of its own height in a single night has spent 2 centuries gradually rebuilding pressure within itself. Volcanologists do not believe another eruption on the scale of 1815 is imminent, yet they understand that the possibility cannot be dismissed across longer spans of time. Geological systems do not follow human calendars. Their rhythms unfold across generations, centuries, and millennia. For the people who lived around Tambora before the eruption, the volcano was woven into ordinary existence long before it became a global disaster. Volcanic soil enriched crops and supported dense communities. Forests flourished across the slopes. Rivers carried minerals down from the mountain into fertile lowlands. The same forces that eventually destroyed entire kingdoms had also spent centuries sustaining them quietly. Life near volcanoes has always involved this exchange. Creation bound tightly to destruction, abundance resting beside instability. Even now, the caldera itself reflects that dual nature. Rainwater gathered within the immense depression formed a crater lake over the decades following the eruption. Vegetation returned gradually along the ash covered flanks. Pioneer plants rooted themselves in barren ground, followed by shrubs, then forests dense enough to hide much of the devastation beneath green growth. Ecological recovery did not erase the violence of the eruption, yet it demonstrated the patient persistence of living systems shaped by volcanic landscapes. The processes beneath Tambora today are the same processes that once generated the immense pressure wave heard across oceans, the sulfur veil that dimmed sunlight around the world, and the pyroclastic flows that erased entire communities in hours. None of those forces disappeared when the skies eventually cleared. They remain part of the planet's interior machinery, moving invisibly beneath rock and water beyond the reach of human memory. The Earth does not preserve grief in the way people do. Mountains rise, collapse, refill, and rise again according to energies far older than civilization itself. Beneath Tambora's quiet crater lake, the planet continues its slow internal motion, steady and indifferent, breathing through stone beneath the sleeping forests of Sumbawa.